Hello boys and girls, welcome again to another science video lesson, and this is Sir Ryan, and for today's video lesson we will going to talk about what are the mechanism that drives the continents or plates in motion. So we will discover what are this process, the mechanics of how this plate movement possible. Okay, so let's discover that one today here in our science video lesson. All right, so this is the question that we were going to ask before we discuss the topic that we have today. What drives plate motion? This is the same question that was asked to a geologist, all right, after he discovered the mechanism that the continents of this planet has. All right. So during his time, he was asked this question: What drives the plate motion? So obviously, during that time, he has no idea how this one works and how this one is possible. He doesn't have any idea of processes and mechanism on how to do that. So people or the scientific community during that time didn't accept his idea about how the continents move from one place to another. But today we're going to find out what is this mechanism that enables us to have the plate tectonics theory that I featured in the last video lesson that we had. All right, so let's take a look. All right, so our video lesson or the topic that we have today has something to do with this baggage conveyor. So as you can see here, this is found in, or this is this conveyor belt that you have right here is placed in an airport. Okay, so the baggage are seated there, then it circulates around. All right, so the baggage are circulating around in this conveyor. All right, so aside from that, we have here the treadmill. All right. So as we all know, in order to use this treadmill properly, you must move in the opposite direction of the movement of the treadmill itself. So you must move in the opposite direction. Then the faster the treadmill, the faster the movement that you need to do in order to not to crush, all right, at the end of this treadmill, because when you follow the direction of motion of this treadmill, you will likely to crush on this on the other side, so on this side. All right, so that is the treadmill, and we have here the escalator. Right, so if you are familiar with the escalator, these are things, or these are machines that are found in malls, in some establishments, and they are used to lift people from one level to another. So as you can see here, when you ride this escalator, your body follows the movement of the escalator. Okay, so if you try to counter the movement of the escalator, it will give you a hard time to do that one. For example, the escalator is moving up and you want to go down, so it will give you a hard time. Okay, to do that one. So it needs, or it requires a lot of effort. So what are these things? Why are these things connected to our lesson? Because it has something to do with what they call the idea of conveyor belt. Okay, so it has something to do with conveyor belt. So as you can see here, whenever a people or whenever a person ride on one of these, especially this, except for this one, this is baggage. All right, so whenever an object rides on these machines that we have right here, it somehow follows where the machine is moving. All right, so it follows the direction of the machine where it is moving. So basically the same thing that is happening on Earth's landmass. So the landmass here on Earth, the lithosphere to be exact, is following the movement inside, right? So it follows the movement of the mantle material inside the Earth. So how does it work? So in this lesson, we will going to find it out today. Okay. All right, so what drives plate motion? So there are several models that explains this mechanism, but none of those model, right? None of those model explains before. All right, so before that was before. None of those model perfectly explains on how they work. So that is why in the middle of 19th century, all right, or 20th century, in the middle of 20th century, there are the scientific community doesn't have any idea on how this one works. All right, so until such time that there are already some instruments like seismic tomography, sonar, or something like that, they be able to distinguish and identify how these large plates move from one place to another. So the second bullet that we have right here is the Earth's heat is the reason why the plate moves. So this is the driving force, right, in this mechanism. So in short, this Earth's heat that is coming from the Earth's core is the one that drives this process, okay, that drives this process and enables the plate to move from one place to another. So without this heat that we have right here, the Earth's heat, there will be no movement of plates that will going to happen. All right. So there are several models that has been proposed, and one of those is the SLAB-PULL and SLAB-PUSH model. So what are this one? Okay. So if you recall our previous video lesson about types of plate boundaries, so this type of plate boundaries has something to do with our topic today, because one of them is the convergent boundary. Now, in the convergent boundary, there are events that is happening on that type of plate boundary, which is part of the mechanism of plate motion. That is the descending oceanic crust and pulls the plate downward. Alright, so this is the convergent type of plate. And what place in the convergent type boundary? So that place is called the subduction zone. Alright, so there is no place in the convergent type plate boundary where an oceanic crust will descend other than the subduction zone. Alright, so the next one is the divergent boundary. Right. So why do we know, right? Why do we know that this is a divergent boundary? One thing, because there is no type of boundary that has a ridge system. Right? So there is no plate boundary that has a ridge system other than the divergent type boundary. All right. So that is the slab pull and slab push model. So let's take a look on what does it look like in a diagram. So it looks like the one that you have right here. So this is the slab push and slab pull model. Okay, so the slab push starts from the oceanic ridge that you have right here. Right, so whenever a new material that comes from the mantle, gets out of this volcano at the middle of the ridge, so it pushes away the material. Okay, the material that is old enough is pushed from the side and it moves away from the center. So as it does, all right, so as it does, it encounters on the other side, all right, it encounters on the other side a subduction zone, which is part of the convergent boundary. And on that subduction zone, there's a slab pull. All right, so there's a slab pull, the descending oceanic crust, which is more dense than your continental crust over here. All right, so the more dense plate or the denser plate will likely to subduct below the continental plate. So that subducting plate will be pulled downward to the mantle with the action or with the help of gravity. So with the help of gravity, slab pull will be possible. All right, so that's the reason why these two movements that you have right here, must be present at all times. If must be present at all times, and what will likely to happen if one of them is absent. For example, if only ridge push is present here, the earth will likely to grow bigger. the earth will likely to grow bigger because it will be continued to be supplied by more materials that is coming from the mantle. And if there is no subduction zones or slab pull that will be done on this part of the subduction zone over here, right? So what will happen here is the earth will grow bigger. All right. Now, if only there is a slab pull, there will be no material that will be left on your ocean floor. There will be no oceanic crust that will supply the ocean floor. So therefore, the ocean floor will likely to be emptied. Alright, so it will likely to be emptied, and the only material that will remain here on Earth are the continental crust. Okay, so there will be no oceanic crust if only slab pull is present. So as you can see here, the lithosphere, alright, above, follows the movement of the mantle. Just like your escalator, your treadmill, and your conveyor belt found on the airport, the lithosphere is riding above the flow of your mantle. So whatever flow of the mantle dictates, the lithosphere will just follow. All right, so that is this is the model of slab pull and ridge push, respectively. All right, so aside from that model, there are also several models that are proposed, especially on the process involved in the inside the earth. Okay, so the first one here is the plate mantle convection. Okay, so these are some idea. These are some idea that that is gave by some geologists about how the earth, okay, what is the behavior of materials inside the earth. So what is this plate mantle convection, and what is this convection all about? All right, what is this convection? All right, so remember that convection is just one of the three ways of heat transfer. All right, one of the three ways of heat transfer. The first one is the conduction, that is a contact heat transfer. Example, when you put a spoon on a hot water, then eventually after a few minutes, the spoon will become, will get hot. All right. Next, the second one is radiation. Radiation is a non-contact heat transfer. Example is the heat that is coming from the sun that travels several million kilometers to the earth, and all the things here on earth will feel that heat that is coming from the sun even though it is a million kilometers away. So that is radiation. Okay, so what we have here is a convection. This is also a heat transfer, but in solid, rather liquid and gases. All right, this is the convection. This is the heat transfer done in liquid and gases, and it involves the following things. All right, so in convection, you have your density. It depends on the density, and also it depends on the heat, the amount of heat, all right, present in a certain area. So technically speaking, convection leads to unequal heating. All right, so convection leads to unequal heating. All right, so later we'll just show you how this unequal heating is done here inside the earth. All right, so according to some geologists, that these mantle plumes, they have an idea that these mantle plumes are the extension of the mantle core boundary. Right? These are the extensions of the mantle core boundary, and it causes the convection process. All right? These things causes or triggers the convection process in the whole mantle. Okay, so in the whole mantle plumes are part of this process. Now, there are several models that we have right here. Okay, so we will going to have that one later. So, but before that, let's have this demonstration. Right, so let's watch this demonstration on how does a convection process happen. Possibly the same thing happen inside the. Okay, so let's watch this one. So,
Miss, welcome again to another science demonstration. For today, we will going to demonstrate how convection inside the earth happens. So let's check it out. This demonstration, so we will going to use the following materials. So we have a chalk, powdered chalk. So we have here the oil, and we have the beaker, we have the iron stand, and we have the wire gauze. Then we have the alcohol lamp, and finally we have a lighter. So these are the materials that we were going to use in our demonstration today. Set up, what we will going to do is to put the powdered chalk at the center of the beaker.
All right. So as you can see there, right. So as you can see on this particular setup, so we have here the okay. So we have here the cooking oil and then the chalk at the center. So the cooking oil represents the mantle material. All right. So this represents the mantle material, and the chalk at the middle represents the rocks. All right. The molten rocks that are found in this mantle. All right. So aside from that,
What we have right here. Then we put the cooking oil. Alright, we put the cooking oil inside without disturbing the powdered chalk at the center. Then we put the alcohol lamp below below our setup that we have right here, and in this demonstration we will try to somehow simulate how convection process happens. Okay.
all right. So we have here the alcohol lamp as part of the setup, and it represents the heat that is coming from the Earth's core. All right. So you can pause this video if you want to. So I have a question right here. So what will happen if there is no heat that is supplied by the alcohol lamp? So what will happen in this overall process? You can write it down in the comment section for your answer, then unpause the video after that. Okay, so again, what will happen if you remove the heat, the source of heat that is coming from this alcohol lamp in this setup? So what will happen to this setup? And the second question is, what after this demonstration, what will happen to the oil itself? All right, so what will happen to the oil after this demonstration? Okay, so let's continue.
So at this moment, the chalk particles that are located at the center of this beaker is starting to move upward as the heat from the alcohol lamp continues to supply our setup that we have right here. So what do you think is happening?
All right, so again, you can pause the video to answer that question. So what is happening right here? Hey, so what is happening right here on this at this point in this particular setup that you watch over here? Yeah. All right. So after this after several minutes, so we notice that there are a lot of particles that are starting to go up. Okay, so remember that convection depends on the density of the material. So what happens to the density when the material gets heated? So the material became less dense. All right, when they became less dense, they became buoyant. Then they float upward. All right, so they float upward, and what will happen next?
In this situation that we have right now. Okay. So on the top view, here we have the chalk particles that is moving from coming from the center. Then they are moving from the center to the side of this beaker.
All right. So after moving to the center, coming from the center, then moves up. Then, as you can see here, there are particles that is starting to move to the side. Right. So it starts to move on the side. And what do you think is happening here? All right. So you can pause this video and then write it down in the comment section. Okay, what is happening right here? What makes what do you think? All right, what do you think is the process going on in this particular area on the side of this beaker?
So what do you think is happening on this event that we have right here? as the heating continues, the clear oil that we have earlier is now cloudy due to the chalk particles that circulates inside the cooking oil. So as you can see here, we can't see anymore the chalk particles that we set up on the middle of this beaker. And when we look on the top view, okay, as you can see here, there are chalk particles that are moving on the side of this beaker.
All right. So, okay. The reason why it is moving on the side of this beaker that you have right here. So, before we have that answered. All right. So, if you answered that the oil will become cloudy at the end of the demonstration, you are correct. All right. What makes it become cloudy? That is because of the process convection. Now, in the convection process, all right. So, in the convection process, when the object is heated, it became less dense. Then it goes up. Then, as you can see here, from the center, the materials or the particles migrate to the side. Because on the side of this beaker, where there is a this particle starts to cool down. All right, starts to cool down on this side because this is the side of the beaker this is the side of the beaker in which it is not heated. All right, by the alcohol lamp. So technically speaking, there is unequal heating that is happening in this setup that we have. Okay, so as it cools down, it goes to the side, then it became more dense once again. Alright, so it became more dense once again, then it sinks at the bottom, then the cycle continues. Right, so the cycle continues. So less dense, it floats, then it goes to the sides, it cools down, then it sinks, then it goes back again to the center where the heat is present, then it floats up, and then so on and so forth. Okay, it is a cyclic pattern. All right, it is a cyclic pattern that is happening inside this beaker. Okay.
So what do you think is happening here? The result of our demonstration that we have here. So as I remove the heat coming from the alcohol lamp.
All right. So in this case, in this demonstration, I removed the heat. Right. So I removed the heat from the setup. So as you can see here, there are no. Okay. What is remaining here is the small amount of heat. It will continue to do the convection process, but in a slow pace. All right. So it will do the convection process, but in a slow pace, and eventually, if the heat runs out, the convection process will cease on this setup. So it will cease, then it will be a completely cloudy oil that we have right here.
So the cooking oil became cloudy, and there are a lot of particles that are present on the top of this setup that we have here. So this is the okay. So these are the chalk particles that moves from the center. Then after that, it moves to the side of this beaker.
All right. So that is a simulation. That is a simulation on how possibly, all right, possibly the convection process inside the earth happens. All right. So okay, let's go back to our main screen. Right, so that is the convection process. Okay, so again, the convection depends on density and then the amount of heat that you applied in a certain liquid or gas. Okay, gas objects. Yeah. All right. So that is the mantle. That is the convection. Okay. So now, in that particular demonstration, it showcased how the materials, when they are heated, they become less dense, and when they cool down, it sinks. All right, it sinks at the bottom, and the cycle continues. All right, the cycle continues because there is an unequal heating present in your system. So please take note that in the convection, unequal heating Alright? Unequal heating is happening. Okay. So, there are models that we have right here that will help us explain how this plate mantle convection happens. Alright. So, okay. Now, let's try to find out what are the ideas of this model and what are their shortcomings. Alright, so that we will be able to find out what makes them advantageous or what makes them not advantageous to use. Alright, so okay. So the first one is layering at 660 kilometers. All right. So layering at 660 kilometers. So as you can see here, the upper mantle has its own process of convection, and up at the 660 layer, or at 660 kilometers, which is the boundary between upper mantle and then the lower mantle that is located somewhere over here, there is another process of convection that is only present in the lower mantle. So as this convection happens in the lower mantle, it affects the material on the upper mantle. And not only that, okay, so not only that, the subducting plate, according to this model, is stops until 660 kilometers. Right? It stops at 660 kilometers over here, and the material which subducted mixes with the material in the upper mantle that you have right here. So, the main idea of this model is that whatever material that sinks to the upper mantle will be the same material that will come out of the oceanic ridge. All right? If this is basalt, all right? So if this is basalt, which has a certain chemical composition, it will be the same thing over here. It will be the same thing over here. It has the lava that will come out in this ocean ridge will have the same chemical composition as the one that's subducted. Right. Whereas the materials that comes out of the hotspot, the one that you have right here, the materials that will come out of the hotspot will be completely different from those material that is coming out of the ocean ridge. Alright, so they will be completely different in terms of chemical composition. Because this hotspot over here, this mantle plume, right? So this mantle plume over here originate down to the lower mantle. Alright, so down to the lower mantle, which has completely different composition between the upper mantle. Okay, so lower mantle and upper mantle have different composition. So the mantle plume, alright, the mantle plume that you have right here, the materials here will be the same as the material from the lower mantle. So that is its main idea, right? That is its main idea. The lava that are found in oceanic ridges are different than those in Hawaiian Islands. So Hawaiian Islands is a hotspot. Remember our last video lesson, all right? The testing the plate tectonics theory. So it talks about the hotspot, all right? So it talks about the hotspot, and it has different chemical composition, all right, compared to those lava that are found in the oceanic ridges. But there is a shortcoming with regards to this layering at 660 kilometer. There is a shortcoming or loophole. All right. Now, according to the data gathered using earthquake waves, all right. According to that data, the subducting ocean slabs can penetrate beyond 660 kilometer. Alright, it can penetrate beyond 660 kilometers. So if we will go back on this diagram, so it doesn't stop right here. So it can penetrate greater than 660 kilometers. It can go down there. So meaning to say, if that is the loophole of this model, alright, geologists created another model that will address this loophole. So according to them, the convection, alright, the plate mantle convection model should be like the one that we have right here, the WHOLE-MANTLE convection. Now, this WHOLE-MANTLE convection model addresses the loophole of the first one. So, right now, or the subducting plate that we have here right now, can penetrate now beyond 660 kilometers. Alright, so it can penetrate now beyond 660 kilometers, and there's no individual convection process. The whole mantle itself, from the name of the model itself, the whole mantle itself is doing the whole convection thing. All right, so it does the convection process, the basic convection process. The denser material, when they are heated, they go up, then they cool down on the side, and it sinks at the bottom when they completely cool down, and the cycle continues. All right. Now, the one that we have right here at the middle of the in each of the convection process, that is the hot spot, or that is the mantle plume. All right. So the mantle plume signifies that the material that are being heated from the core mantle boundary will go up and eventually form a hot spot over that area. All right. So it seems like there's no loopholes with this one. All right. It seems like there's no loophole, but according to some study, all right, according to some study, that if the subducting slab, all right, if the subducting slab will likely to mix in the whole mantle material that you have right here. So as you can see here, eventually it will mix over this mantle material over here. It will mix down. All this material coming from the subducting slab will mix down through your mantle material over here. Okay. Yeah. Right. So I just push down the eraser. Okay. So if you okay, so this particular subducting slabs that you have over here, okay, so that subducting slab over here, okay, will have, okay, this whole mantle that you have will have the same material as this subducting slab after a few million years. So okay, according to that study, all right, according to that study, that after a million years, after 100 million years, it will completely mix up with the material of the mantle. Okay, so what will happen here is the material that will be ejected out, the material that will be ejected out of the hotspot will be the same material that will be ejected out in the oceanic ridge. Both of them will now have the same material, okay, of the lava that they will eject out. Okay, so that is the loophole of this model. Okay, so that is why geologists develop again another model that will address this loophole and develop this deep layer model. Okay, now in this deep layer model, okay, so we have two separate convection process. One is from the parts of the upper mantle, all right, and the lower mantle, the upper parts of the lower mantle. Okay, and the next one is the lower mantle facing the core. All right, so the lower mantle facing the core, that is the second convection process. So as you can see here, that part, all right, so that part of the lower mantle, when it is being heated, it swells like the one that you have right here. But if the particular place, when they are cooled down, all right, when they are cooled down, it shrinks, right? It shrinks like the one that you have right here. Now, over that process of shrinking and swelling, okay. So again, it addressed the subduction zone or subduction slab that you have right here, the subducting slab that is until or greater than 660 kilometers, but not, okay, not passing through this particular boundary that you have right here, this boundary of the lower mantle. Okay, so the subducting slabs is until that point, all right, and it will be completely mixed up with this material that you have right here. But the idea of having chemically different material that is ejected from the hotspot will stay the same. All right, will stay the same because the one that will go out, the material that will go out of the oceanic ridge, the one that will be ejected out of the oceanic ridge, will be the same material as the one that subducted your on your mantle. Okay, so whatever materials that you have right here is the same with the oceanic ridge. So, okay, it will not contradict that particular idea. Okay, so that is the no, that is the good thing about this deep layer model. But hey, there are still loopholes on this model. But as at this point in time, all right, at this point in time, currently, or the geologists are investigating it further, all right, for this loophole. Okay, so hopefully that this particular model doesn't have a lot of loopholes, all right, on it, so that we will now have a somehow precise model that will clearly explain how this convection happens inside the Earth. All right. So, to answer the question, which model should we follow? All right. I think there is no model that we should follow. All right. I think there's no model that we should follow. Every model that you have seen a while ago are good in their own ways. All right. They are good in their own ways, and although there are shortcomings coming from them, but some of them clearly explains certain phenomenon that is happening on here on Earth with pertains to that particular model. Okay, but there's one thing, okay, there's one thing for sure. Those three models that we have discussed earlier, those three models follows the same exact process, and that is convection. All right? It follows the process of convection. It doesn't contradict the direction of motion of your material, the mechanism of convection. It doesn't contradict that. Those three models, whatever models that we use, right, regardless of which, still follows the convection process. Okay, so this is our somehow keyword on this video lesson, convection. All right, so before we end up our video lesson today, so let's have this summary. Number one, the two mechanisms that contributes to the convective flow are the following. So we have the slab pull, all right, with the action of gravity. With the action of gravity, the oceanic crust that is subducting, all right, on the subduction zone will be pulled back to the mantle, and the ridge push, as long as there are new materials that is coming out from the oceanic ridge, all right, it will be completely pushed aside on that particular area. So these two things that we have right here, all right, contributes to the plate motion. Right? So it contributes to the plate motion. Right? So the next one is, all right, hot buoyant mantle plumes are considered the upward flowing arms of mantle convection. All right. So the key idea here is the mantle itself is doing the process of convection, and what is convection all about? That is a heat transfer. All right, heat transfer in liquid and gases. And convection depends on the density, all right, density and the amount of heat present in a certain system for it to do this particular process. All right, so remember that less dense material, when the material becomes less dense, it is heated up, and when the material cools down, it became more dense, and then uh, it sinks again, then the process continues in a cyclic pattern. That's how convection process works. And lastly, we have the three basic models of mantle convection. We have layering at 660 kilometers. We have the whole mantle convection, and we have the deep layer model. So just remember, guys, there are no models that are perfectly designed to explain how mantle convection works. Besides, no one had been yet on the mantle. All right, no one yet traveled down the mantle, so we cannot describe how this convection happens work. But the good thing here is whatever model that you use, it still follows the idea of convection. Alright, so it follows that idea of the convection or this heat transfer that we have right here. Alright, so to answer the question, what drives the plate motion? Alright, so to answer that question, what drives the plate motion? I hope this particular question was answered by the scientist, right? By the scientists who proposed that the continents are moving. Okay, I hope during that time he discovered this certain process to completely explain his work. All right, so to answer that question, what drives plate motion? The answer there is the unequal heating inside the Earth's interior. Okay, that is what driving the plate in motion or the lithosphere in motion. All right. So with that, if you learned something from this, lesson that we have, so give yourselves a high five. High five, guys. High five. All right. Okay. So with that, that ends up. I guess that ends up our video lesson. All right, for today. Okay. So all right. So I hope you did learn something from our lesson, the mechanism of plate motion. Okay. So if you learned something from this lesson, just hit the thumbs up. All right, in this video, and subscribe. Then click the notification bell. Okay, for you to be updated with more science video like this in the future. Now, if you do have question and if you do have a suggestion on what kind of video do you want me to create in the future, just write it down in the comment section. Okay, so don't forget to subscribe and like the video. It will help me a lot in the process. All right, so that ends up our video lesson today. Stay safe, guys, and let's see each other to the next science video lesson. Goodbye, guys.